In this video, we will talk about properties of coefficients of regression. We know that if numbers a, b, c are in proportion and if a upon b equals b upon c, then we can write b square equals a into c, where b is called geometric mean of a and c. On the same lines, coefficient of regression y on x into coefficient of regression x on y gives us, for b yx we write coefficient of correlation r into sigma y by sigma x into, for bxy we write r into sigma x by sigma y. Here this sigma y cancels with this one and this sigma x cancels with this sigma x, and we get r square, which is similar to b square equals ac. That is coefficient of regression y on x into coefficient of regression x on y equals square of the coefficient of correlation r. So this is our first property. Byx into bxy is r square. So the first property of coefficient of regression is coefficient of correlation r is the geometric mean between the coefficients of regression byx and bxy. Since a squared quantity is always positive, both byx and bxy will be either positive or both byx and bxy both negative. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. We know that coefficient of correlation lies between -1 and +1. Squaring this expression, we get 1 less than or equal to r square less than or equal to 1. Since r is a proper fraction, its square will also be a proper fraction. Hence, r square cannot be greater than 1. So finally, what we get is r square less than or equal to 1. But we have just seen r square is byx into bxy. Therefore, their product will be less than 1, which also means byx is less than or equal to reciprocal of bxy. So naturally, if this byx is less than 1, this bxy got to be greater than 1. So this gives us the second property of coefficients of regression. If amongst byx and bxy, if byx is less than 1, then bxy is greater than 1. Similarly, if bxy is less than 1, then byx is greater than 1. So this is the second property. We will find arithmetic mean of both the coefficient of regressions y on x, that is byx, plus coefficient of regression x on y, that is bxy, and half of it is always greater than coefficient of correlation r. Now let us prove this statement. So we write half in place of byx, we write r into standard deviation sigma y upon standard deviation sigma x plus r into standard deviation sigma x upon standard deviation sigma y greater than or equal to r. Dividing throughout by r, this r cancels with this r. That will be sigma y by sigma x plus sigma x by sigma y greater than or equal to this 2 multiplied by this 1, which will be 2 here. Further, this will be sigma y into sigma y square plus sigma x into sigma x square upon sigma x into sigma y greater than or equal to 2. This further will be sigma x square plus sigma y square greater than or equal to 2 times this sigma x into sigma y. This further will be sigma x square minus this 2 sigma x sigma y plus sigma y square greater than 0. Now this is a perfect square quadratic polynomial which can be written as sigma x minus sigma y whole square, whose expansion is this left hand side expression, and it will be greater than or equal to 0, or it will be non-negative. Now this is very much true because square of any real quantity is always non-negative. Since this last statement is true, it goes to prove our third property, arithmetic mean of coefficients of regression bxy and byx is greater than or equal to coefficient of regression r. This property can also be stated as sum of coefficients of regressions bxy and byx is greater than or equal to 2 times coefficient of correlation r. Suppose coefficients of regression are b1 and b2, and if arithmetic mean of b1 and b2, that is b1 plus b2 upon 2, is p, and difference between b1 and b2, that is b1 minus b2, is 2q, what will be the coefficient of correlation r? From b1 plus b2 upon 2 equals p, we get b1 plus b2 equals 2p, and we have b1 minus b2 equals 2q. We write it here. Adding this, b2 minus b2 will be 0. 2b1 will be 2 times p plus q. After cancelling these two, we get b1 equals p plus q. Using value of b1 in this first equation, we get p plus q plus b2 equals 2p. b2 will be 2p minus p minus q, that is p minus q. Now we have coefficient of correlation r equals square root of b1 into b2, that will be square root of p plus q into p minus q from these values of b1 and b2. That gives us r equals square root of p square minus q square. So this is the value of coefficient of correlation in terms of p and q. Let us investigate whether the lines 2x plus y equals 3 and x equals 2y plus 3 can be the lines of regression. If we write this first line y equals minus 2x plus 3, then it becomes line of regression of y on x, and its coefficient of regression byx will be this minus 2. This line obviously is the line of regression of x on y, whose coefficient of regression bxy is this 2. In the first property of coefficient of lines of regression, we have seen that both byx and bxy must be either positive or both must be negative, and both should be less than 1 numerically. But here they are greater than 1 numerically. Therefore, these two lines in this form cannot be the lines of regression. If we write this first line as line of regression of x on y, it will be 2x equals 3 minus y, or x equals minus half y plus 3 by 2. And if we write this second line as line of regression of y on x, it will be 2y equals x minus 3, or y equals half x minus 3 by 2. Here the coefficient of regression bxy is this minus half, which is numerically less than 1, and coefficient of regression byx is this half, which is numerically less than 1. But since they are of opposite signs, negative and positive, which does not satisfy the condition of this first law. Hence, both these lines 2x plus y equals 3 and x equals to y plus 3 cannot be the lines of regression. X plus 3y minus 5 equals 0 and 4x plus 3y minus 8 equals 0 are the two lines of regression. We have to find coefficient of correlation R. First, we will assume this first line to be the line of regression of x on y, which will be written as x equals minus 3y plus 5, and the second line of regression of y on x can be written as 3y equals minus 4x plus 8 or y equals minus 4 by 3x plus 8 by 3. Here the coefficient of regression bxy is this minus 3, and here coefficient of regression byx is this minus 4 by 3. So we write r equals square root of bxy into byx, which will be square root of minus 3 into minus 4 by 3, that is square root of 4, or r will be 2. But r cannot be greater than 1. Therefore, our supposition that this is the line of regression of x on y and this one is line of regression of y on x is wrong. Now we will consider this first line to be a line of regression of y on x, so that 3y will be 5 minus x, y will be minus 1 by 3 x plus 5 by 3. Here coefficient of regression byx will be this minus 1 upon 3, and we will consider this second line to be the line of regression of x on y, which can be written as 4x equals minus 3y plus 8, x equals minus 3 by 4 y plus 8 by 4, that is 2. Coefficient of regression bxy will be this minus 3 by 4. So in this second case, we will find out coefficient of correlation R equals square root of byx into bxy, which will be square root of minus 1 by 3 into minus 3 by 4, which will be square root of 1 by 4, or the coefficient of correlation will be half or 0.5. Since coefficient of correlation is less than 1, this line of regression of y on x and this line of regression x on y are the true lines of regression. Next we will find angle between the lines of regression. We know equation of a line of regression of y on x is y minus y bar equals byx into x minus x bar, whose slope m1 is byx, which is r times standard deviation y upon standard deviation x. Similarly, equation of line of regression of x on y is x minus x bar equals bxy into y minus y bar, which can be written as this y minus y bar equals 1 upon bxy into x minus x bar, where slope of this line m2 is 1 upon bxy, which is 1 upon r times sigma x by sigma y, which further will be sigma y upon r times sigma x. So we have slope of line of regression of y on x m1, which is r into sigma y by sigma x, and slope of line of regression of x on y m2, which is sigma y upon r times sigma x. Now if theta is acute angle between the lines of regression, then we have tan theta equals m1 minus m2 upon 1 plus m1 m2. Substituting the values of m1 and m2, we get r into sigma y by sigma x minus sigma y by r times sigma x upon 1 plus r times sigma y by sigma x sigma y by r times sigma x. Tan theta equals r square sigma y sigma x minus sigma y sigma x upon r sigma x square upon this r cancels with this r, sigma y square plus this sigma x square upon sigma x square. This will be taking sigma x sigma y common multiplied by r square minus 1 upon this r sigma x square multiplied by this sigma x square upon this sigma x square plus sigma y square. Now this sigma x square cancels with this sigma x square. Since we are interested in finding the acute angle between the two lines, we will take tan theta equals mod of this whole thing. So that gives us freedom of writing this as, instead of r square minus 1, we will write 1 minus r square for convenience upon this r into sigma x sigma y upon sigma x square plus sigma y square. Now we understand various interpretations of the formula tan theta equals 1 minus r square upon r into sigma x sigma y upon sigma x square plus sigma y square. In the first case, if r is 0, tan theta will be infinity, therefore theta will be pi by 2 radians, and in this case the lines of regression perpendicular to each other, x equals x bar and y equals y bar. Second interpretation is, if r equals plus or minus 1, tan theta will be 0, which means theta will be 0 and the lines will be coincident. The lines will be coincident like this when r is plus 1 and coincident like this when r is minus 1. In the third interpretation, when theta is small, that is nearer to 0, r will be nearer to 1 because there is high degree of correlation and the lines will look like this with small angle of theta between them. And the fourth interpretation is, when theta is large, that is nearer to pi by 2 radians, r will be nearer to 0 and there will be low degree of correlation and the lines will look like these with large angle between them. If we are to find the angle between the lines of regression with the help of the data given sigma x equals 4, sigma y equals 5 and coefficient of correlation r equals 0.6, if the angle between the lines is theta, then we write the formula tan theta equals 1 minus r square upon r into sigma x sigma y upon sigma x square plus sigma y square. It will be 1 minus 0.6 square upon 0.6 into 4 into 5 upon 4 square plus 5 square. That will be 1 minus 0.36 upon 0.6 into 20 upon 16 plus 25, 41. This gives tan theta equals 0.52 and theta will be 26.56 degrees. In the next sum, suppose standard deviations sigma x equals sigma y, which is sigma, and the angle between the lines of regression is theta equals tan inverse 3. Since theta is tan inverse 3, tan theta will be this 3 here equals 1 minus r square upon r into sigma square upon sigma square plus sigma square 2 sigma square. Sigma square cancels here and we get 1 minus r square upon 2r. After cross multiplication, we get 1 minus r square equals 6r, or it will be r square plus 6r minus 1 equals 0. We will solve this quadratic equation by quadratic formula. R equals minus 6 plus minus square root 6 square minus 4ac, that is 1 into minus 1 upon 2a, that is 2 into 1 2. This will be minus 6 plus minus square root of 36 plus 4 40 upon 2. This will be minus 6 plus minus 2 root 10 upon 2, which will be minus 3 plus minus square root of 10. So finally r will be minus 3 plus minus square root of 10, 3.16. So r will be 0.16 or minus 6.16. This second value is rejected because numerically it is greater than 1. So the final value of r is 0.16. If you like this video, please like it, share it, and subscribe to this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.